5.6, working with complex numbers. Now, remember back that we were told that no negatives in even radicals, that they are D and E. They do not exist. And that's true, they do not exist. But there's a method that we can use called the Imaginaries. So imaginary answers, or imaginary roots, they use the letter I to represent that negative value. So before you can tackle anything, just remember that there are situations. So basically, I represents the square root of -1. And if we do I squared, means I squared the radical and I get -1. So I and I squared are going to be very important features of this section. So it says express -5 times the square root of -49 as a complex number in terms of I. So you're going to take your original problem. And before we even knew about imaginaries, you saw a -49 inside a radical that's even indexed, and you would tell me does not exist. And it doesn't, because it does not exist, it does not hit the x-axis. But for this one, they incorporated the imaginary values. So what we're going to do is we're going to isolate that negative. So I'm going to rewrite this problem as -5 times the square root of 49 times the square root of -1. All I did was isolate the negative to its separate radical piece. So we still have -5. Now I can take the square root of 49, that is a 7. Remember what I said earlier. I represents the square root of -1. This is -1 in the radical. That represents the letter I. All you have to do is finalize your mathematics here. So -5 times 7, that is -35. With an I attached, now you are in complex answer. Next problem. So it says 3i times -8i. So they want us to do the product. So you do 3i times -8i. So first thing, let's isolate our numbers together. So I'm seeing 3 times -8, and then I get I squared because there's two i's, an I to the first, another I to the first. Think of your base rules. If bases are the same, which these are the same base, you add your exponents. They both share an exponent value of 1, so that's where we got our two pieces. So we do 3 times -8, that is -24. Now remember, earlier I said I is square root of -1, and I squared is just plain -1. So now this I squared is being substituted by the -1 value. Now we can apply the product rule here. So -24 times the -1 makes it +24, and you are finished. Next example. They want us to evaluate an expression that says -8 minus 1i plus 2 minus 7i. And it's going to result in an a plus bi, which happens to be, if you think about it, it's a type form of the conjugates. We used conjugates earlier when we were talking about radicals in the denominators. So in this instance, we have your original problem, -8 minus 1i plus 2 minus 7i. So when you come to problems like this, remember, it's a plus sign. There's space. It's not being product. This is a space value, so you're adding. It's the sum of the parts. So you're adding like terms. So you have two options. You can group your pieces, which I'm going to do right now. So I'm going to write -8 because that's a -8. It's a +2, and I'm adding a +2. There's a plus sign. -1i, -7i. I grouped my pieces. So -8 and +2 is -6. -1i, -7i is -8i. That's what I had as my answer. That was one way. You just grouped your complex pieces, which are the ones that have the I attached, and your real pieces, which is the plain numbers. So the other way is you just bring everything out with like terms. So that's +2. Remember, you distribute the positive in. And again, you combine your like terms. -8 and +2 gives you -6. -1i, -7i, -8i. I received the same solution. Now, If he went to graphing, this is known as the real part because it's a plain number, and if it's an I, that's the imaginary part. So if you were to graph this on an XY coordinate plane, this real part will be on the x-axis. The imaginary part, you look to the y-axis. Instead of labeling like the y-axis, it's known as the I-axis in that instance. So the y-axis becomes the I-axis. Next example. Okay, on this one it says evaluate the expression 3 plus 4i times. It's the product of -1 plus 3i. So since it's a product piece on this one, I'm going to use the box method. So I'm going to write my box. Okay, so remember you put a multiplication column in the left corner. So we have +3, +4i, -1, +3i. So we're going to apply the product rule here. So 3 and -1 is -3. 3 and +3, +9i. 4i and -1, -4i. +4 and +3 is +12i squared. I'm going to bring everything out that's in this bottom quadrant. So we see -3, +9i, -4i, +12i squared. When we combine like terms, 9 minus 4, because they have the same attachment, makes it 5i. Remember the rules. I is square root of -1, but I squared is plain -1. So I'm going to substitute in a -1 here. So we get -3 plus 5i, +12 and -1 is -12, and then combine your final like terms. So I'm short $3 and short another 12. I'm short 15 plus 5i, and that would be your final answer. Next example, it tells us to do 1 plus 4i over 6i. So on these type of problems, when they're asking you to do the quotient, you're going to use your conjugates. So if I tell you a plus bi, you're going to multiply by a minus bi. If we are given a minus bi, then we're going to multiply by a plus bi. So we take our original problem, which is 1 plus 4i over 6i. We're going to multiply by the conjugate of the denominator. Remember, it's always going to be the denominator. So I'm multiplying the top and bottom. So if it's positive 6i, it's going to be negative 6i. You're trying to get rid of that I value. So we come here, we're going to do a top line, and we have negative 6i times 1 plus 4i. Apply the distributive property. So we get negative 6i, negative 24i squared. Remember, I squared is your -1. So we have negative 6i, negative 24 and negative 1 makes it positive 24. Just rewrite it so that the real portion comes first and then the imaginary part second. So this becomes 24 minus 6i. That is the numerator line. That is what the numerator line became. Then we go to the denominator line, so the bottom. We have 6i, and we multiply it by the conjugate of negative 6i. So that gives us negative 36i squared, which remember, I squared is -1, so we get negative 36 times -1, makes it positive 36. So we're at that point, which means we have to simplify by reducing. So we have, think of it as 24 over 36 minus 6i over 36. 24 and 36 are factors of the number. 36 is 6 and 6. 24 is 6 and 4. They are also the values of 12. 12 goes into 24 2 times. 12 goes into 36 3 times. I get 2/3. Minus 6 and 36 reduces to 1i over 6. So there is our simplified answer. Next example. Okay, continuing again. So it says 3 plus 6i over 4 minus 2i. Again, we're using the conjugate in this situation. So we have 3 plus 6i, I'm putting it in parentheses, divided by 4 minus 2i. Remember, you're multiplying top and bottom by its conjugate. So if it's 4 minus 2i, I'm going to use 4 plus 2i. So we're at that point. So we have a top line and a bottom line. So we're going to work with the top line first. So we see 3 plus 6i times 4 plus 2i. I'm going to use the box method. Put multiplication dot. So we have 3 positive 6i, 4 positive 2i. So we multiply. This is 12. This is positive 6i, positive 24i, positive 12i squared. So we see 12 plus 6i plus 24i plus 12i squared. Remember, I squared is -1. So we change that I squared to a -1 and combine like terms. So 12 and -12, they're going to cancel each other out. 6i and 24i, that makes it 30i. So that's what we get for the top line. When we look at the bottom, we have 4 minus 2i times 4 plus 2i. And back earlier when we were factoring, this is known as difference of squares, which is the a squared minus b squared pattern. So I know what a is. A is a 4 and b is the 2i. So I'm going to put 4 squared minus 2 squared I squared. I split each of the variable pieces here to be its own power. So now we become 16 minus 4, and then remember I squared is -1. So we get 16 minus minus makes it plus 4, giving me 20. So the denominator is a 20. Now we're at this point, and then we just reduce to 3/2 I. So in this instance, since we had 3/2 I as our answer, and they want they want the solution in the form of a plus bi, since we did not have a real portion, a place value holder has to be held for it, which is 0 in this instance. So our a value would be 0, and our b value is 3/2. It's just the value of the coefficient, a and b. Next example. So in this one, they want us to figure out what is the value of I to the 49th power. So when you come to problems like this, when they just want to know what is it, I to the 49th power, remember the patterns. I is square root of -1. If I square it, I get -1. Now, if I do I to the 3rd power, well, I to the 3rd power is actually I squared times I. So we get -1 times I, which is -I. If we do I to the 4th power, that's the same thing as saying I squared times I squared. So we see -1 times a -1, which makes it +1. The reason I'm showing you this is that if you know these 4 original pieces, you know the power of any of these. So the trick is take your original and change it to a base power of inside value of I to the 4th raised to a power. So you want to think about it as how many times does the number 4 go into 49? So remember, 4 goes into 49 12 times. That's 4 times 12, that is 48. With an additional I value, there's my 49th piece. Well, the reason I did I to the fourth is because I to the fourth is the value of 1. The positive 1 raised to a power of 12 times an I value. So 1 times itself 12 times is still a 1 times an I, so your answer is I. And it works with any of them. As long as you use the value of 4, I to the fourth power, how many times does that 4 go into the exponent value C, and you can change it that way. Next example says, find the product of 8 minus 9i with its conjugate. So they didn't tell you what the conjugate is. Remember, if they gave you 8 minus 9i and they want you to use the product with its conjugate, they want you to do 8 minus 9i times 8 plus 9i. So in this instance, we're using difference of squares, which is a squared minus b squared. So for this instance, our a value is an 8, our b value is a 9i, so I'm going to do 9 squared, I squared individually. 8 squared is 64, 9 squared is an 81, I squared is negative 1. So we still have 64. Negative times the negative makes it positive 81. And we're adding 64 and 81, and we get 145. So if they want the answer in the form of a plus bi, well, the a value is 145. 0 is the b value because it does not exist. Next example. Here again, they want us to do the product of 3i times negative 10 plus 2i. So you take your original, and we can use the distributive property here. So negative 3i and negative 10 makes it negative 30 with an I. 3i and 2i is positive 6i squared. Remember your rules. I squared is a negative 1. So we get negative 30i. Positive 6 to negative 1 is negative 6. But we want to be in the form of a plus bi. So we're going to rewrite this so we become negative 6 minus 30i. Next example. Again, it says they want us to final answer as a complex. So it says 2 minus 12i times 2 plus 12i. So first thing I noticed, these are conjugates, which means difference of squares, which means a squared minus b squared. So 2 squared minus 12 squared I squared. So we become 4 minus, it's 144 times negative 1. 4 plus 144, so we get 148. So our final answer would be 148. If they want it in the form of a plus bi, then you would do 148 plus 0i. But I would just leave it in the 148 as an answer.